also reduce the local series expansion or any analytic function, which in turn yields the fact that the derivative of, first of all, the fact that any analytic function has derivatives of all orders, and all the derivatives are also analytic functions. And then we prove the Morira theorem, which is a kind of converse to the theorem of Cauchy. Says that if you have a continuous function, so that the integral of the function along every triangle in the domain vanishes, then the function is analytic. In fact, the function has a primitive and therefore is analytic by what we had said earlier. Then what we had, of course, the Cauchy's estimates for the derivatives of an analytic function, which in turn gives you Liouville's theorem that an entire function which is bounded must be a constant. And also the fundamental theorem of algebra, saying that any complex polynomial has a zero, must vanish at some point in the complex plane. If you have a function, analytic function, whose derivative vanishes, a function is a constant provided your domain is connected. But if you look at what we wrote, the statement was this, but the proof was for something else. So we'll redo that now, so there's a correction there. So today we'll look at more consequences of all this, power series expansion and so on, Cauchy's estimates, etc. Say something about the zeros of an analytic function, and you'll also see that analytic functions are rigid in some sense. So, for example, if a function vanishes in some small part of the domain, it vanishes identically. What is the small part? We'll make precise. In a subdomain, for example, if a function vanishes inside a disk in the domain, then function must vanish identically on the domain. In fact, much stronger than this. So in particular, for example, this is again in total contrast to the case of real valued smooth infinitely differentiable functions. I'll make more comments on this when we come to that. So let us start with two statements. Suppose f is analytic in omega. Omega, okay, f is then both. Each of these sets is both open and closed. Set of points where all the derivatives vanish, this is open and closed, and set of points where the function takes the value uh, at same as the value of f at a fixed point there. See, they are both open and closed. So, in particular, if omega is connected, it will deduce something. Okay, so essentially, the first result was proved yesterday, right? When I stated the result as if prime is 0 identically, then function is a constant. So it was proved yesterday. If you remember, we looked at this set. Okay, E is because by definition, when n is equal to 0, the function is f itself. So don't include that. So this is open and closed, was proved yesterday. It's closed because zeros of continuous functions are closed sets. So the intersection of all zero sets of each fn there. So proved yesterday. So let us try to prove the second one. Take z naught and look at all points where the function takes the same value as f as of z naught. It's again obviously closed because again by continuity, just a continuous function pulls back closed sets to closed sets. So you have a singleton set f z naught. So this set is closed, whatever you want to call it. To see that it is open, suppose take a point A in that set, we want to find a neighborhood of that point which is contained in E. Right? Every point of E is an interior point. That's what I want to show. So choose a disk around A. Is contained in the disk omega. So look at the disk. So this is A. So what do we have to show? We have to show that for every point in the disk, this holds, right? So you have A. So take any other point in the disk. look at the line segment joining the 2 points that is inside the disk, of course, because the disk is a convex set. Call this point as Z. So the line segment joining A and Z is given by 1 minus T times A plus T times Z, right, for T lying between 0 and 1. So this gives you all points in that segment. Okay, so if Z is in the disk, so let us call it D. Okay, that is in D, then the line segment joining A and Z is this. So let's define a function on interval 0, 1. So we can, f is differentiable, and of course this function is differentiable as a function of t. So we can differentiate phi with respect to t. So what is the derivative? Use the chain rule, right? Derivative of f at this point multiplied by the derivative with respect to t of this. So f prime so if you differentiate this with respect to t, what do you get? Z minus a. Minus a. So let me modify the second statement. Make this additional assumption that the derivative of f is 0. Then for any z naught, this is both open and closed. Okay, so what do we get now? This is 0. So what is the conclusion? You have a function defined on the interval 0, 1 with derivative 0. So that function must be a constant by mean value theorem, for example, right? Therefore, phi is a constant on 0, 1. So phi is a constant. So for example, therefore, phi of 0 equal to phi of 1. Okay. So what is phi of 0? It is f of a. Phi of 1 is f of z. But what was a? We started with a in E. That means f of a is equal to f of z naught. So this is f of z naught. So what have we got now? So at some point a f of a is equal to f of z naught, then whole disk there f of z equal to f of z naught. So which is what, and by saying that the whole disk is contained in E, therefore E is open. So now if you assume that omega is connected, so what can we conclude from these two? Suppose omega is connected. What do you get from the first one? If you have a connected set, the only open and closed subsets are the empty set and the whole set. So if you assume that omega is connected, the first set is either empty or it's the whole thing, right? So what does it mean? If the set is non-empty, then it is a whole thing. The set is non-empty means what? At some point z naught, all the derivatives are 0. Then the conclusion is all the derivatives are 0 at every point, right? If what does this mean? The function is a constant, right? If you look at power series about any point, the coefficients are all given in terms of the derivatives, right? If you have then an is something like that, okay? So if all these are 0, only the constant term a0 survives, right? So the function therefore reduces to a constant. What is the conclusion in the second case? Omega is the whole thing if it is not empty. So that means at every point z, f of z is equal to f of z naught, which means again that f is a constant, right? So for a non-constant function, for example, in a connected domain, not all derivatives can vanish. So let us look at now possible sets of points where the function can vanish. But before that, probably let's prove Weierstrass theorem before that. It's going to be a consequence of the Morira theorem, so let's finish that. See, in real case, real analysis, we have a sequence of continuous functions which converges locally uniformly on every compact interval. Then the limit function is also continuous. Right, but this is not true for differentiability. For differentiability, you need uniform convergence for the derived differentiated sequence. Okay, but in the complex case, you don't need this additional thing. Just uniform convergence will give you differentiability for the limit function also. In other words, uniform limits of analytic functions are analytic. This is the Weierstrass theorem. Because in complex function theory, there are so many theorems called Weierstrass theorem. So specify what theorem that we are talking about. If a sequence Fn of analytic functions omega converges locally uniformly means uniformly on compact subsets or equivalently uniformly on closed disk inside omega to function f, then f is analytic. In other words, local uniform limits of analytic functions are analytic. Moreover, the differentiated sequence, that is Fn prime, also converges locally uniformly to F prime. Once you say that F is analytic, F prime exists, and we can say that Fn prime converges locally uniformly to F prime. And of course, you can keep differentiating. All the derivatives exist, and the kth derivative of Fn converges to the kth derivative of F for every k. Because once you know that F is analytic, we know that all derivatives exist. So the first statement is immediate from Weierstrass here. You want to say that F is analytic. Okay, so by Weierstrass theorem, it's enough to show that integral along any triangle is 0. But integral of F along a triangle is limit of integral Fn along the triangle because of uniform convergence. but fn's are analytic, and therefore those integral fn over the triangles are all 0. That's all. Okay. So that the interior also because of uniform convergence we can integrate. Because of the uniform convergence on the triangle, so this is by Cauchy's theorem for a triangle. And therefore so now just invoke Weierstrass theorem to so that's all. There is nothing immediate from Weierstrass. But you can also see this directly without appealing to Weierstrass theorem if you use the integral formula. The advantage in the second proof is that you can use it for the derivatives also. So this proof cannot be used to get the second statement here, and this convergence of this. Okay, so for any zeta in omega, you look at the Cauchy integral formula in a suitable disk around zeta. F of zeta is 1 over 2 pi I integral over whatever c zeta r right, for a suitable circle around zeta. I mean, not this. For fn's, we have to show that f is analytic, right? So this doesn't hold for f to start with. So Hn. Now you can take the limit. What do you get? On the left hand side, you are going to get f of zeta. On the right hand side, you are going to get the same thing with f in place of fn. Again, you can integrate because of uniform convergence. So taking limits, I get how do you conclude from this that f is analytic? What did we do yesterday? Starting from the Cauchy formula, we got the power series expansion by writing this suitably, so on. So you can start with this integral there and get the power series expansion for f. And so conclude that f is analytic. In a disk, inside any disk in omega, so in the whole of omega. So this remark that I wanted to make, but I forgot. When we proved that result, starting from the Cauchy formula to conclude analyticity, what we had was this, right? And then from this we got the power series. All that was needed was the analyticity of f. So you define of f of zeta as, I mean, 1 over 2 pi a is not necessary, I mean, for analyticity, right? If you have a function like this, where phi is an analytic function, then you can do the same thing, whatever we did, starting from the Cauchy formula, except that the difference here is instead of phi, f, the function f, you have a function phi. In other words, start with a function which is analytic, phi, and define f by this integral whenever it makes sense, then f is analytic. Okay? In other words, the Cauchy integral of any analytic function gives you an analytic function. So if phi is analytic, and we define f by this, then f is of course you have to make lots of qualifications for a suitable C, etc., etc. So phi is analytic in the neighborhood of. So anyway, so from this we can conclude that f is analytic. So this. Now, whatever we did for the function f here, the sequence fn, and for f, you can do for the derivatives. You can look at fnk, you have the integral there, take the limit. So for any k, Right? This is the formula for the derivative, right? The kth derivative and so the by taking limits huh? K factorial somewhere. K factorial here. Okay. So the kth derivative of fn converges to kth derivative of f. This is no problem. But how do you get uniform convergence in compact sets? That I'm not going to write out, but I'll tell you. Okay. So what you have to do is you look at, instead of writing this, taking limit, you get this. You take the difference. Okay. So saying that by uniform convergence, take the limit, is actually estimate the difference, take modulus here, and write down an estimate on a suitable disk. You will therefore get uniform convergence. So if you get uniform convergence on every disk, you get local uniform convergence. Okay. So estimating, I will just write the right side. I can get uniform convergence on every disk. Which is same as local uniform convergence. All F is suppose Z naught is a 0 for F. That means F of Z naught is 0. So if you look at the power series expansion around Z naught, so in a disk around Z naught, F of Z is F of Z naught, or so F of Z naught is what? So the constant term in the power series is 0. Look at A1, next coefficient. It may be 0, it may not be 0. A1 is not 0. Z0 is called a simple 0 or 0 of order 1. So you can keep, if A1 is also 0, look at the next one. So you can look at the smallest k for which AK is not 0. So in general, suppose so that means so A0 etc. up to AK minus 1 are all 0 and AK is not 0. AK is the first non-zero AN. Then you say that it is a 0 of order K. So what happens, how does the power series look like in that case? Fz is sigma An right? All the earlier terms are all. So the first term is the kth power, AK z minus z0 to the k. So it starts the kth power. So we can pull that out and write this as z minus z0 k to An n minus k. Correct? So what about this factor here? That's a power series, right? And therefore gives you an analytic function in that disk. So call it GZ. GZ is given by this power series where GZ analytic in that disk, of course. And what is the value at Z0? It's AK, right? Which by assumption is not 0. So G of G is analytic and G at Z0 is non-zero. So if you have a continuous function which is non-zero at some point, then in some neighborhood of that point, the function is non-zero. G does not vanish in a neighborhood of Z. So in this case, what can you say about the derivative of f at Z naught? Coefficients are all in terms of the derivative, right? An is fn Z naught by n factorial. So from an is 0, that fn is 0. So what do you get in this case? Not only f of Z naught is equal prime so on a minus 1 all the derivatives up to k vanish at Z naught. Kth derivative does not vanish. The kth derivative is in terms of k. So this k saying that Z naught is a 0 order k is equivalent to saying all the derivatives up to order k, up to order k minus 1, and 0 and so on. But the kth one is not. So all this under the assumption that a0 is 0, a1 is 0, ak minus 1 is 0, but ak is not 0. So there is some an for which an is not 0. We are taking the smallest such k. Suppose there is no such k. Meaning what? Suppose all the derivatives at Z naught are 0. That is fn nth derivative of f at Z naught is 0 for every n. Then what we said earlier, remember the first result that we have set of all points where fn is 0 for every n, that is open and closed. So if your domain is connected, is the whole thing. So if there is some point where it is holds, then it holds everywhere. So in other words, if you are looking at a connected domain, such a thing does not happen. Right? Unless the function is a constant. Right? If omega is connected, okay, and f is not a constant, then it cannot happen that fn is 0 for every n. Right? There has to be some k. Yes. In other words, if fn, see, if up to k minus 1 it is 0 and at k it is non-zero, you call it as a 0 order k. So if it is 0 for every k, every n, then it is what you can call as a zero of infinite order. Right? The what we said just now says that in a connected domain there is no such thing. Zeros of infinite order do not exist. Right? So if omega is connected, then f of z naught is equal, then there is the k such that this holds. F is a zero function. So in that case, of course, everything is of infinite. Z naught is zero of order k. F of z is z minus z naught to the k times the function g, where g at z naught does not vanish, and therefore g does not vanish in a neighborhood of z naught. Which means, so what is the conclusion about f in that neighborhood? So g does not vanish when any z not equal to z naught in a neighborhood. So what does that say about f? F also does not vanish at any other point, any point other than z naught, right? In that neighborhood, in some neighborhood of z naught, where g has no zero, and therefore f has no zero other than z naught. Z naught is the only zero of f in that neighborhood. So what do you say in this case? Topological term. Point 0 is isolated, right? There is no other zero in a neighborhood. So the conclusion of this statement can be expressed by saying that the zeros of an analytic function are isolated ones. So f has the neighborhood something n of z naught, so g of z naught is not equal to 0. G of z is not does not vanish in a neighborhood n of z naught, and therefore f has no zero other than z naught in n. So in other words,
So the set of zeros of analytic function is an isolated set of points. Such a set has to be countable. So the set of zeros is countable discrete. Because countable means it can be empty or finite. Or countable. So the set of zeros is countable discrete. Because countable means it can be empty. For example, the exponential function has no zero. The whole set. The set is empty. For example, the exponential function has no zero. The whole set is empty. What about sin z? Where does the sign follow sin z? Where does the sign come from? All multiples of so if one now here as one infinite, okay. So if one now here as infinite. So you can say if you count what's the screen, you can say that it has exactly ends because counting. Suppose you can say if you count one screen, you can say that it has exactly ends because counting. 0, 1, 2, count twice.